and we're live on YouTube, so you're ready to go. Have a good session.
Excellent, thank you. You see my screen fine, right? You don't see my Zoom window on top of it.
Correct.
Excellent, good, great. Okay, welcome back everyone from this short break for the next session, which is the Test of Time Awards ceremony at CHES 2021. And it's my pleasure to chair the session, to host the session. So this session obviously is about the Test of Time Award. This is something we started quite recently, namely last year in CHES 2020. And the idea is, well, the same as all over IACR. We would like to kind of, appreciate a paper that has a lasting impact on the field, both ideally in academia and in industry. The models that we kind of what we selected is that we have a sliding window of 3 years. So and we papers that were published at CHES within those 3 years are eligible to be nominated, and then from those papers there's a committee that makes a selection. Okay, so the window goes back from 21 to 19 years. So this year it's CHES 2000, CHES 2001, CHES 2002. Those papers are eligible. Anyone is able to nominate. Okay, there's this yearly rotating committee that makes the ultimate selection. This committee is formed by 2 members who are appointed by the CHES steering committee, and by 3 invited members who ideally are, program committee chairs from those years of CHES, or members of the program committee or something like this. And we also strive to have at least 1 member from industry, because as I said, impact in industry is also something that we would like to assess somehow. You can see all the details about everything here on this webpage about the Test of Time Award. For this year, the committee was composed of the following people. There was Ingrid Verbauwede, Jean-Sébastien Caron, who actually was a PC member in 2001 and 2002, and actually also received the award last year. There was David Nakash, PC chair 2001, PC member 2002, Berg Sunar, who was a sub-reviewer in 2001 and a PC member 2002, and then myself. So I would like to thank all the committee members for their effort and for the work in selecting the paper. Okay, and so ultimately we answered the big question. The award goes to, well, it's a paper from CHES 2001. It's written by Louis Gauvin, and the award is for his paper, A Sound Method for Switching Between Boolean and Arithmetic Masking. So, congratulations to you, Louis.
Thank you.
I will say a few more words. I just have to switch my screen quickly because my trick here doesn't work. All right, so so a little bit of background. As you just saw, the paper is published at CHES 2001. So think back to that situation. DPA was rather new. It was, I guess, rather a shock. Well, not only DPA, but the whole power analysis story was probably a shock for the industry, and people were looking for countermeasures. Some were quite ad hoc. And also remember, people were still learning about DPA itself. So 2001, that's pre-CPA era, right? It was all single bit or maybe multi-bit DPA or something, but it was pre-CPA era. Okay, so for most of the PhD students who are now listening, that's probably hard to imagine how that was. Anyhow, so masking had just been recently proposed as a new and sound method for protecting cryptographic software implementations, and it could quite easily be applied to algorithms if it was possible to rewrite the algorithms in such a way that they worked on masked inputs and produced masked outputs. And that worked well for some of the algorithms, but it didn't work for all of the algorithms at that time. For example, it didn't work for some of the AES candidates. And again, go back and remember, this is 2001, so the competition had just finished. It didn't work for IDEA, and it didn't work for SHA-1. These algorithms mix Boolean and arithmetic operations. So we need different kinds of maskings, and we also need methods to convert back and forth between them. There was a solution that was earlier proposed by Messages, and then was shown to be insufficient to protect against DPA. And so Louis went ahead and wrote this paper in which he proposes two new algorithms to convert back and forth. And these algorithms are provably secure against DPA. Okay. And so if you compare this statement, provably secure against DPA, you will see that, so two questions today would be provable in which model and provable against exactly which DPA. But I guess at the time, DPA was always first order DPA, right? There was no strong drive towards higher order things. So things have evolved. It turned out that Boolean to arithmetic conversion is quite easy, and that arithmetic to Boolean conversion is somewhat more involved. I'm sure Louis will speak about that. So we selected this paper because, not because it has the highest citation count, it doesn't, from the papers that were nominated. But we also took into account that this is a very, very niche topic. This is a very small niche topic within the field of masking. It's a small niche, but considering the small size of the niche, the citations are high, and the impact that the paper has high. I'm going to speak about that in a moment. The paper today has around 180 citations on Google Scholar, and we see that the follow-up work, is always about people trying to, find flaws in the existing algorithms, or try to improve them, try to make them more efficient, extend them to higher orders, and so on. And this is a line of work that has been going on consistently over 20 years. And today, the paper finds a completely new application field in the masking of post-quantum algorithms. You have seen it probably cited several times in the first session on post-quantum crypto on Monday. So this clearly demonstrates the long-term impact of the paper in academia. It's also a short paper, which is something I would like to highlight. It's a paper that the main body of the paper is 9 pages. Okay, so a good paper doesn't have to be long. It's hard to say something about the impact of this paper in industry. I hope Louis will speak about that a little bit. But so at the time when this paper was written, Louis was working for Schlumberger, as far as I could figure out, which later became Exalto and today is Gemalto. Therefore, I guess the motivation for the work came from industry. I found 9 patents that cite this paper. 6 of them are by smart card companies, including Louis' first patent on the topic. Okay, and now I would like to give the floor to Louis. Please share the screen. The floor is yours.
Really? Is it okay for my screen?
Yes.
Okay.
You go to presentation mode. We still see the slides bar on the left. So if you push F5, then your presentation starts.
I'm trying to do that. Is it okay now?
Yes.
Okay. So first I would like to thank the TestofTime committee and the CHES 2021 organizer for this great honor. I am very happy and proud of having this old paper nominated and accepted for this award. It's a bit strange to think about a 20-year-old paper, but I think it's a good idea to remember this paper and to see what consequences it can have on the current research. So this is a paper. So as Benedict mentioned, at this time I was working in Schlumberger. CP8 was the former name, and it had many names later: Exalto, Gemalto, and now it's even not Gemalto, it's Thales. The latest name is Thales. So yeah, CHES 2001 was in Paris at this time, and as Benedict summarized, all the story was about differential power analysis. So Benedict mentioned the model in which we were. And so basically we were in a very first model of DPA, and what we were considering is the fact that each intermediate variable during a computation could or not depend on key bits. And so the danger was when the intermediate variables were depending on a few key bits, not all the key bits. And that's what made the attacks possible and still make them possible. But it was basically the model in which we were, and we tried to avoid this problem by changing the way of implementing the algorithm, so that each intermediate variables did not depend on too few key bits. So several countermeasures existed, of course, already at this time. You remember that the first CHES edition was in 1909, and we proposed at this first edition of CHES the duplication method with Jacques Patarin. And there was also the Crypto 99 paper by the IBM team, which proposed a kind of similar method to counteract power analysis attacks. And Tom Messerges, as Benedict said, also proposed specific methods for the AES finalists, so in FSC 2000. And what happened is that the method proposed by Messerges had still some vulnerabilities, and we pointed out these vulnerabilities with Jean-Sébastien Coron in CHES 2000. In CHES 2000, we showed that there were still problems in the Messerges method, which was already dealing with the problem of converting between Boolean and arithmetic masking. So the masking, as you all know, is the idea of basically splitting all the intermediate variables into several variables, so that each one individually, in the case of the first order DPA, has a random distribution. This makes the first order attack, for instance, impossible. And if we iterate this principle, we can make the task of the attacker grow exponentially in the number of shares, whereas the defender task is still linear in the number of shares. And so this is a basic idea, but if we want to implement it concretely, we face some difficulties, because many algorithms do not use only Boolean or only arithmetic functions, but mix the two of them. And so, for instance, all these first slides are taken from my presentation at CHES 2001. So at this time, we were considering AES candidates such as Mars, RC6, Twofish, and there was also IDEA in the field. And the problem is that they use both kind of operations, Boolean and arithmetic, and so we need sometimes to have Boolean masking, sometimes to have arithmetic maskings. These are here on the formulas. And the problem is thus to convert from one kind of masking to the other one and backwards. And this was exactly the problem we studied at this time. So I will not enter into the details, but so these are notations, but basically the main probably the main discovery was that this function, so the function here, which consider a constant and then XOR the constant with the variable and then subtract the variable, everything is computed modulo 2 to the k. This function doesn't seem to be affine, but in fact it is. It is an affine function over GF2. So this was surprise. Many people were very surprised by that. Some were not believing it was true, but it is. If we try to prove it, it's not difficult. But it was a big surprise to discover that this function was affine over GF2. And when you know that this function is affine, in fact, it's exactly the function that is suited for the Boolean to arithmetic masking. So you just have basically to use these functions, introducing a random value in it to convert between one kind of masking to the other one. Basically, you have to compute x prime XOR r minus r in a DPA resistant manner. And to do that, you introduce a random value gamma here, and you compute all this. And this is the same result for A, for big A, because of the affine property of this function. And since you introduce this random value gamma, you can prove that what we did, you can prove that it is indeed resistant to DPA in the first order. So this gives a very simple algorithm, which is written here. It's only a few XORs and subtraction here. So this was the first direction, and the other. And this requires 5 XOR instructions and 2 subtractions. For the other direction, arithmetic to Boolean, it's a bit more difficult. We had to use a recursion formula. It's not only one formula. You have to iterate the formula, and this iteration has to be done on a number of times, which is the number of bits of the registers you are using in the variables. So this is the formula. It's again, it can be proven. It's not so easy to prove, but you can do it when you want. And this gives the same kind of idea. You can use this recursion formula by introducing again a random variable. And it can be proven again that if you introduce this gamma random variable, everything during the recursion formulas remains resistant to first order DPA. So the algorithm looks similar here. There are XOR, and it's also use AND operation and doubling also. And but here you can see there is a loop. The loop is exactly corresponding to the fact that we have a number of operations and computation time which is proportional to the size of the registers. So you can see it here. There are 5k plus 5 elementary operations. K is the size of the registers. So this is a very brief summary of the paper, and the conclusion of the talk in 2001 was okay, that we did that, and an open problem was to try to improve it, especially the direction arithmetic to Boolean was not very satisfying if the size of the registers became bigger. At this time, there were many, for instance, smart cards with 8-bit registers, but it was clear that we were going to 32 bits registers, and so it was becoming more and more important to do that. So in the next slide, I try to cite some more recent results that were inspired by this paper and this question at the end of the paper. So the first direction was to improve exactly what I said, to improve the performances of this conversion. So the first idea by Jean-Sébastien Coron and Alexei Chulkin was to use some kind of time memory trade-off. So they proposed several at CHES 2003, they proposed a method based on pre-computed tables, and there were many subsequent papers improving the size of these tables. And then there was I would say, a big discovery in FAC 2015 by Coron, Groth-Schellel, Tibucci, and Vadnala. And they showed that the arithmetic to Boolean was doable with only a logarithmic complexity. So it means log of k instead of k operations. They used a specific adder, the Cog-Stone adder, which is a variant which allows to use a carry not one bit after another, but several bits at the same time. And it was also a bit improved in Cardis 2017 by Biryukov, Dinu, Lecor, and Yudovenko, with some between 14 and 19% improvement of the speed. Another direction was to generalize all these conversions for higher order DPA. So this was studied also by Jean-Sébastien Coron and others. I cannot cite all the names, but you see them on the slide. In more recent papers, CHES 2014, CHES 2017, 18, and the Journal of Cryptographic Engineering in 2019. The question of the proof was also important. As I mentioned, the reason I was interested in this problem was the fact that there was a vulnerability in the messageless method, but the messageless method had no proof. So that's a sign that proofs are important. So my paper had a proof, as I mentioned, and there were some other problems later. For instance, the table-based method by Coron and Chulkin had a bug which was found by Blandine Debrez in CHES 2012. And she proposed a fix, but there was another flaw in the fix flow found recently by Van Beirendonck, Danvers, and Ingrid Verbode in this year in CHES 2021. And higher order generalizations, as mentioned before, were proven in the ISW framework for private circuits. And I finished by some applications. So there are obvious applications which were already clear at the time in CHES 2001 for block and block ciphers. Sorry, stream ciphers should not be there. Block ciphers, as I mentioned already, including ARX constructions, hash functions. So there were many use of these methods for implementing hash functions, and of course, more frequently it was HMAC functions because we need a key for this being interesting, and also stream ciphers. And more generally, at CHES this year, there is a paper, for instance, about an instruction set extension to support generally masking in a software context. And this includes the problem of converting between Boolean and arithmetic. And for more recent applications, so there was one in CHES 2006 by Proof, Giraud, and Aumonier, based on Fourier transforms to secure S-box implementations against DPA. So this used as a tool the conversion between arithmetic and Boolean. And more recently, as Benedict already mentioned, there are some use of these conversions for public key cryptographic algorithms. There was one at Eurocrypt 2018, the GLP lattice-based signature scheme at any order, and and also some post-quantum candidates For instance, this year, this paper about the protection of cyber against side channel attacks. And last word, maybe it could also be, there are some similar problems if you want, for instance, to consider white box implementation. For instance, the CHES, one of the two CHES 2021 challenges was about implementing white box ECDSA. And if you dig into the problem, you see that ECDSA also uses different structures, algebraic structures, the one about the elliptic curve, and then you have to switch to integers modulo the cardinal, the number of points of the curve, and this also creates some problems if you want to mask everything. And so there are some ideas coming from the conversions also arising in this kind of problem, which are specific to white box, because ECDSA is easier to protect in a classical DPA setting than in the white box model. Okay, so that's what I was happy to say about this paper, and thanks again for choosing this paper. Thank you very much.
Thank you very much, Louis. Nice recap of what happened. So we started a little bit later, so therefore I think it's also fine if we go a little bit over time. If there are any questions, I'm not keeping an eye on the Zulip chat, so if you have questions, please, I don't know, just unmute yourself and ask, or write them here in the chat. And we can take a look at those. Otherwise, I would still come back with my question, impact on industry. I know it's hard to say something about that, but okay, so we know you were working in industry, so I guess this was a,
yeah,
I mean, a real work problem and not just some hobby.
Yeah, so the impact in the industry is yeah, it's never easy to understand, because there are some secrets of company secrets about that. But as you mentioned, there are also patents that were filed for this methods. So it's the first thing is that it protected, for some companies, it protected their way of implementing it, and it was really used for some algorithm. Especially, I know that for the HMAC implementation, it was often used to convert between Boolean and masking in this way, or in derived ways. So it's an important application for HMAC applications. For yeah, so for DS or AES, I'm not sure it was so important, because there were other ways of dealing with the problem. But yeah, it's because yeah, you can use other representations of the S boxes. There are many ways of dealing with the problem. But yeah, it was important, and as I mentioned, and probably it's going more and more important now for the post-quantum lattice-based, basically, candidates. But it's less sensitive question, because the patents, as you chose 20 years for the test of time, it means that the patents are over. So yeah. It's exactly
the patent duration. Yeah. So you were 20 years too early with your work.
Probably.
Okay, so we have two other questions in the chat. The first one is it possible to obtain a similar affine map modulo a prime? So not just the power of 2?
I don't know. No, as far as I know, it's not possible to directly obtain something similar for primes. So it has to be studied differently. Here, all the method is based on a very specific property of integers modulo 2 to the k. So it's yeah.
Okay. And the other question is, can we get an algorithm for A to B that is independent of the word size for first order, just like B to A?
We don't know. It's an open problem. It's the best we can do at the moment is log of k, and we don't have a proof that it's impossible to be in constant time with respect to the size of the registers. But yeah, we don't know. It's an open problem.
Okay, thank you very much again. Congratulations for the award.
Thank you.
I suggest we stop here. We do 5 minutes break and then start almost on time with the next session.